Okay, so hi, I'm Lisa Lippincott, and I am here to talk about the vector challenge. Now, this talk is going to be a little different from my usual talks in a couple of ways. One is, in my usual talks, I talk about something that I understand pretty well, and then I complain afterwards that I didn't get a chance to talk about things that I don't understand very well with people after the talk. So today I'm being a little different in talking about things I don't understand very well. This is a talk about problems to a large extent, but also some solution directions. This one's also a little more personal than my regular talks. So I'm going to start by talking about me. And particularly my education. I went to college way back sometime, and I studied math and physics and a bit of philosophy, a bit of linguistics, all of which has turned out to be useful in my later life. So hooray for a liberal arts education. And then I went to graduate school in math. And when you go to graduate school, you specialize and you study. So there was a lot of math. Everybody I knew was studying math. You know, you get a cup of coffee, you talk about math. You play cards, you talk about math. You go to dinner, you talk about math. It was math, math, math. But you specialize further as you keep studying. The algebraists specialize in algebra, and they talk to the algebraists, and the topologists talk to the topologists, and the logicians talk to the logicians. That was me. I studied mathematical logic. Not a very big field. There were a lot more algebraists, topologists, and analysts, and whatever. But studied logic, how sentences relate to truth, how proofs work, that sort of thing. And you keep studying, and you keep specializing, and you keep studying, and you keep specializing, until you figure out something new. At that point, you are now the world's expert in some tiny field that nobody else knows anything about. My particular tiny field had to do with these sorts of pictures that category theorists draw when they're talking about categories. They draw these sorts of pictures, and they use them as a formal language. They use them as the sort of thing that logicians study. And so I studied the way they use these as a formal language, and I wondered, well, what's the expressive power of it? Can you do proofs with it? And the new thing that I had figured out was, yeah, you can do proofs with these. You can, in general, do proofs with languages that are made up of pictures this way. Now, these languages had been studied a little before, not much, but there were a few papers from like back in the 70s. But I think the roots I can trace back at least as far as this guy, Ludwig Wittgenstein, who wrote a very short book, the Tractatus Logico-Philosophicus, back...
He disavowed shortly after.
Yeah. He had a complicated and interesting life, and he wrote other stuff later. But in the Tractatus Logico-Philosophicus, which he wrote during World War I, like in between shooting people, he talked about these picture languages and why, and what was so great about them. And the thing that he really liked about the picture languages is that there is a simple and direct relationship between how you say something and what you mean by it. And that makes a lot of difference in a language. So what do I mean by a simple and direct relationship? I mean, if there's an arrow in the picture, that means there's an arrow in the category. It's that simple. And languages that have that sort of property are very easy to reason with as a logician. Now, that's not the first place I had come across such languages. Turns out I had encountered them when I was a child putting together models from Lego bricks. If you've ever opened up a Lego set, it comes with a set of instructions for putting together something. And those instructions are in a picture language. They're just a series of pictures of partially built Lego models. And I discovered Legos when I was traveling with my parents in countries where I did not understand the language. And I was totally floored by this Danish toy whose instructions I could read, even though I didn't speak a word of Danish. So I had been interested in this sort of language a long time. I mean, the category theory thing, I didn't realize it connected until, pretty far into it, but it's the same deal. Picture languages are great because they have this simple relationship between what you say and how you mean. Okay, so that's graduate school. I had become the world's expert in my tiny field. Do you graduate then? No, there's more to it than that. You have to learn to explain your reasoning. You have to write down your explanation, and you have to get somebody to check it. Once you've done all of those things, and that is not an easy task with some new bit of math, but once you've done all of those things, you can graduate. So, did that, looked for a job, did not find one. The market for jobs in math was really tight when I got out of school. And in a tight market, people want the old familiar flavors. And I was doing this weird logic category theory fusion cuisine. So, not having a lot of luck getting hired, I decided to take programming seriously as a profession. I'd been programming for quite a while. I'd been putting myself through school with money that I earned programming. But now I'm looking at, this could, programming could be my profession. And I got, deeper into it. I started giving talks at conferences and, studying things. I was getting ready to join the C++ committee when I met this guy, Alex Stepanov. And one day we had a very long conversation that I think I can, definitely say changed my life. And I'll tell you a couple of things that he said.
He does that.
Okay, you did it for other people? Good. Okay. We talked a long time about our backgrounds, our interests, and programming. And at some point, I had told him that I was thinking of joining the C++ committee. And he asked me, I think, a very sensible question. What do you want to change about C++? And, I had some things. And I said, I think we should have variadic template parameters. That would be a great addition to C++. And he says, yeah, that'd be nice. And got anything else? And I said, I think we should be able to bind values to functions to make functor objects in a nice way, the way that boost bind eventually did, std bind did, and eventually we got lambdas. And I described that to him, and he said something like, yeah, that'd be nice. And I'm thinking, what does it take to impress this guy? And I do have some other ideas, but most of my other ideas are little things. And clearly, I had to go big. But there was something. I wasn't talking to anybody but my closest friends about this one. But it was something I'd noodled on a bunch. And it's a problem that I'd been interested in since college. But, it was just a kind of out there problem that I noodled on sometimes. But I said I said, okay, here is a thing that I've observed. We know why we expect the programs we write to work. I think we should explain our reasoning in a formal language and have computers check that our reasoning is correct. Now, I was not the first person to think this, I think. Maybe I'm the first person to put it so clearly, I could hope. But no, other people had had this idea. But I would go further and say, for C++ programs, that formal language should be C++. Why should it be C++? Picture languages. You get a nice, direct relationship between what you say and what you mean by it. And if you're trying to describe something in a different language, it's really hard to get that relationship. The relationship is much easier if you say things in C++ and you talk about C++ in C++. So I thought that was something we should go for. Now, I do want to say there had been some ideas floating around that were definitely in this direction long before this conversation. It turns out really a lot of the problem comes at the interfaces between different parts of your program. And that had been noticed years before. And in fact, there was a pretty influential language called Eiffel that had this idea that you should, built into the language, that you should express with your function its pre and post conditions. Here, this is popping something from a stack in Eiffel. It's an example from Bertrand Meyer's book. Require is your preconditions. It's a list of expressions that need to be true. Do, that's your function body. It's a list of statements that you do. Ensure is your post conditions. It's a list of expressions that need to be true afterward. Now, I am going to note there's a couple of things to point out here. One is the do part is written in a slightly different language than require and ensure. The do part is statements. Require and ensure are lists of expression. Do part is a list of statements. Require and ensure list of expressions. So a little difference in expressive possibility there. And you also get this weird syntax old for referring to the value that used to be in this variable back at precondition time. You have this special syntax for referring to it. That's a little weird because that's a syntax you can only use in post conditions. So not a perfect picture language, but a good start. And I had learned, a lot from learning Eiffel. I do want to say, as I looked up this example, I came across Bertrand Meyer's 1988 opinion of my project. The ability to formally express assertions of a general nature, powerful enough to describe realistic abstract data types, requires an assertion language in which one can directly manipulate sets, sequences, functions, relations, and first-order predicates with quantifiers, such as for all and there exists. And he goes on to point out, correctly, that those are not really practical things to include in a useful programming language. And he considers this pretty much an insurmountable burden. But I don't. Why do I not consider this a burden? Because I know you can do proofs in picture languages. I had the thing that said, no, you don't need all that stuff. This is like saying that there are some things you can't draw a picture of, like ineffability. I don't know how to draw a picture of ineffability. And if in the process of describing how to put together my Lego model, one of the steps was attach the ineffability 3 studs from the left. I don't know how they would express that without resorting to words. Well, here's the thing. Exactly the same reasons why you can't draw a picture of ineffability are excellent reasons why ineffability is not one of the pieces that comes in a Lego set. There is no ineffability in the box. So I know, yes, if you're used to doing things with all of these tools, then yeah, you reach for those tools, but you don't need them. You can get along just fine without them. And if you get along without them, you can avoid saying certain nonsense, like attach the ineffability 3 studs from the left. You can't say that in a picture language. Oh, what's happened to the projector here?
Did it go to sleep?
No, computer's fine.
Maybe connection?
Did I stay on the same slide too long? Here, I'll
Is the
reconnect.
red box connected?
Cable
Oh, there's a cable.
Oh,
I stepped on the cable. I'm sorry.
Wasn't it?
okay. Is it coming back? No,
The
we put
connection
the
was
tech-
ineffable.
Yes. Okay, we're back. But we should go back into the mode where you can't see what's coming. So yeah, Matt's Bertrand made a good start, didn't believe in the project, didn't create a perfect picture language there. When I went to translate this sort of thing into C++, it took a while, but I eventually settled on this sort of syntax. So here we are following C++ tradition of dividing things into interfaces and implementations. We can put one in the header, one in the CP file. The syntax here is interface on the left, that's your pre and post conditions. Body of the function on the right, that's the implementation. And there is this special implementation line that says, this is the point where the implementation happens. So the parts above there are preconditions, the parts below there are post conditions. And I will note 2 things. 1, procedural code on both sides. It's a picture language. Other thing is, we don't need that old thing anymore. We've got a block, we can declare a variable. That's how we remember things in a program. We declare a variable. So that's our picture language, the picture language I use for describing function interfaces in C++. And you can go back, I think I've got like 10 years of talks at this conference and a few others on various iterations of this and what are the hard parts and so forth. There are some in which I actually show proofs that use this sort of notation, particularly a couple of years ago, I did one called Principia Mathematica, and last year I did one called Why Loops End. And both of those show actual proofs in the course of the lecture, written in this sort of language. So, with this in mind, we have an idea that was a little missing from the Eiffel design of the interface as a single element that kind of sits between the client, the caller of a function, and the implementation of the function. And it sits in between them and flow passes through it. And it sits there because it's explaining the rules by which the client needs to relate to the implementation. But it's procedural now. Procedural code doesn't just express, it does. What does this procedure do? It verifies compliance with the rules. And this is that bit where it's hard to say nonsense. It's hard to say a rule that is fuzzy or too abstract when you have to actually write the code to enforce it. So this is why interfaces can't talk about ineffability, because you can't write code about ineffability. So interface verifies compliance with the rules. But I have more recently come to the realization that there is something a little wrong with this picture. And that's that there's a boundary that we're really not respecting properly when we look at it this way. And that's the boundary between caller and callee that often runs across translation unit boundaries. Having the interface looking at the interfaces in between requires a sort of cooperation between two translation units often, or between two function neighborhoods. And in later years, I have come to the conclusion that that boundary should be respected better. Really, what we should think of this as is a client's interface and an implementer's interface. And the two are usually textually the same, we hope, but they're compiled separately. The client's interface is compiled with the client. The implementer's interface is compiled with the implementation. And really things need to pass through both. So I like this picture better. There is one accidental weirdness about this picture that I don't like, which is when I drew it, I accidentally created diode symbols on the boundary. That's the wrong electronics metaphor. For those of you who know some electronics, the right metaphor, I think, is isolation transformer. This connection isn't like plugging the cable into your phone. It's not that invasive. It's like laying your phone on an inductive charger. The boundary is preserved. One thing runs in a particular pattern, and that induces the other thing to run in a particular pattern because there is some similarity in the way the coils are shaped. So, enough about electronics. We can get back to my conversation with CppNow. And he said a couple of things. One was, and man, this floored me. He said, if somebody could solve this, it could be you. I'm like, wow. That's flattering. This is like going to the village wise man, and he says, and having him say, with that sword forged by your mathematical ancestors, you could be the one to rid the village of the terrible beast that troubles us. And what do you do after a conversation like that? You think, oh, maybe I should put more time into beast vanquishing. Now, I do want to say it wasn't simple flattery there. He was looking at my background and seeing something that I hadn't really realized, which is that through chance or coincidental interests or whatever, I had collected a lot of tools that were very well adapted to exactly this problem. And that was a rare collection. I know about how many, after trying to get a job, I knew about how many logicians there were in the world. Not a lot. I knew about how many were studying proofs done in weird languages. Less, quite a lot less. And I had a very good idea of how many of them were likely to join the C++ committee. And that's me. So, okay, I guess this is my problem now. I do want to say, this lecture is not the lecture about how I vanquished the terrible beast. This is more progress report on the monster vanquishing problem and some notes on why vanquishing monsters is hard. Now, there is one other thing that he said that really stuck with me. And this, he said it almost under his breath, it was a little side remark. It would be really nice to have that for vector. And this is the point in the story where I say that's a big monster. And I'm like, no, doing this for vector would be crazy. Vector is really complicated. It's got these weird rules, and it does all this stuff inside. And it's a template. And it's not a function. Those of you who have been to my talks before, I talk about function interfaces. And that's not because that's the only thing that needs an interface. Everything that you think about as a unit needs an interface. Everything that, any place where your reasoning has a clear inside and outside, you want to have an interface. And yes, when, vector needs to have an interface. But function interfaces are at least a little understood. I could learn from Eiffel on function interfaces. What the heck is an interface to a type? So this one, I already knew if I attacked that right off, I would be in way over my head. 20 years later, I'm still a little over my head. Yeah, that talk was 20 years ago. But can make a start. Say, well, what is a vector interface going to look like? What does the interface to a type look like? Well, I've only got one trick: picture languages. The interface to a type is going to look a lot like a type. And we're going to have, there's a client of the vector type, and it has a client interface to the vector type, and there will be an implementation of the vector type, and there will be an implementer's interface to the vector type, and usually you'll write these two in between the same. I didn't say, there are some situations where they turn out to be different. Indirection is what makes them different. When you have indirection, the client and the implementation don't perfectly agree because you need some room for slack. The client doesn't know exactly what they're working with, and the implementation doesn't know exactly who's going to point to them. So you get two different interfaces there. I should say, what's indirection to a type? When do you when do you use a type without knowing exactly what type you're using? Template parameters. So there are going to be some shades of concept maps here. I don't know if this goes in the concept map direction. It might. We'll see. So you have these interfaces. We're going to use it directly. They'll be the same text. But what do you do with an interface that looks like a type? You instantiate it to make object interfaces. As we're also going to describe the client of the vector object, the interface that the client sees, the interface that the implementer sees, and again, we're going to stick to where they're the same, and the object implementation. So this is suggestive. The type is going to the type interface is going to declare member variables, and there will be one of those member variables in each object interface. And the object interfaces will have various methods that you can call on them which are going to be interfaces to the methods of the implementation. So we have a layout here, just from saying, yeah, let's just do the same thing over again. It worked the first time, let's try it again. So a little syntax. Now, the syntax is kind of obvious now. We're going to say, yeah, there's an interface and there's an implementation. And I'm just going to put that word in just like I did with functions. I do want to stop here, and it's going to be templated, which, okay, that'll be a little annoying, but yeah, we'll deal with it. I am going to stop here and say, you know, I'm not going to talk about allocators. Nobody's got time for that. Let's just not do that. Okay, so what do we put in a type interface? Well, there's going to be a whole lot of stuff. Yeah, if you're a user of this type, you are going to need to know that those things mean those things. And you're going to need access to some these other types. And here I'm going to say, okay, I'll just say these things are whatever the implementation says they are. And, you know, even if you're doing a template, you've got the implementation, you know, the implementation will be around for instantiation. It can be looked up. So that's pretty straightforward. Should maybe I have put an interface for the iterators? Maybe. I got enough problems. But yeah, maybe another time. You can, of course, put some static assertions in here to say some nice things about how the types are limited. Size type is going to be unsigned, but difference type is going to be signed. And there's a few other rules like that that you can assert. So all that's just sort of background stuff. You're waiting for like the meat. What is a method going to look like? Well, here we go. I'll take an easy one. Size is an inspector for vector. You get back a number, you get size type. And it's going to have an interface. It's going to have and the interface, not a lot of preconditions there. Really, if you have an interface to a vector object, that means you can call size. And so no preconditions, there are no parameters. Is there a post condition for size? Well, you know, it produces a size type, that's something. But there is another post condition that we usually don't think much about, which is if I call size, and then I call size again immediately, it's going to tell me the same number. It's not allowed to tell me a different number the second time. Now, there are some situations under which that number will change, but those are well-defined situations. In general, we call it consecutively, particularly. It's going to give us the same number. So there is some expected size, and whatever size returns is going to be equal to that every time. So there's a member variable there. Member variable for our object interface is the expected size. It's, yeah, this is what size is going to return.
Now, Lisa, it was obvious all along.
This is, you know, and of course, if you were going to write code to check that property, that size continually returns the same value, this is how you would write it. You would make a variable and you would say, yeah, it has to return that thing. Now, you don't have to do that for every inspector. You know, it's if you have something like empty. No, you can just say, yeah, whatever, the result is going to be equal to this expression, expected size equal to 0. So we don't need an expected empty. We might write one as a helper function, I suppose. But we can just say, yeah, that expression tells us what we expect from empty. And these together express the relationship between size and empty. If size returns 0, I expect empty to return true. If size returns something that's not 0, I expect empty to return false. So I can reason just from seeing this code. So that's a method interface, and I want to point out something. If I draw that line between caller and implementation, which, and I wish it showed up better, but there's a little shading that's supposed to emphasize that, but I think it's getting washed out by the lights. In between this, on the caller side of the line, we can execute the post conditions of the size method or the empty method without asking the vector for anything further. These post conditions don't actually talk about the vector. They talk about our expectations of the vector. And they talk about the result that came across the line, the function result. They might talk about the parameters, but the thing they don't talk about is the vector itself. The vector itself is somewhere on the other side of the line, and it stays there. And that's a really kind of neat property. Now, we could have a function that has some preconditions. Here's one, operator square brackets. Operator square brackets has both a precondition and a postcondition. Don't worry too much about this substitutability business. That's just equals isn't strong enough for pointers. They have provenance. It's weird. It's a bit of a problem on its own. It's going to be trouble. But it's not trouble I want to talk about today. But what I do want to talk about is, if you look at the preconditions here, usually we think of the precondition of this method as the index has to be less than the size. But you don't write it that way when you're using an object interface. You write it as the index is less than the thing I expect that size would return if I called size. You don't need to make, you don't ask the vector what its preconditions are before to help you evaluate the preconditions before you make the call. And of course you don't. You have to, in order to work with a vector, you have to have this mental model of what state the vector is in order to work with it. You don't, you just make sure it's bigger than the size you expect the vector to have. So that's what the object interface is doing. This data in the object interface are the parameters to your mental model. Except it's not mental anymore. It's in the computer. We're explaining it in a formal language. So the preconditions don't talk about the vector. The postconditions don't talk about the vector. We do have the ability to store some data in local variables in order to remember stuff from precondition time to postcondition time. It's all very nice. We can explain how square brackets works. So let's make it a little more complicated. Vector throws us some curveballs. One of them is there are two operator square brackets. This one's weird. This one is weird because it looks like a modifier, but we need to treat it like an inspector. This is a non-const method that doesn't change anything. And we have to put some weird wording in the standard to deal with this. Actually, there's a paragraph about how there are certain methods that on the containers that aren't const, but you get to treat them like they are const, and you can't get into race conditions and all that stuff. We need to get that information into the formal language without putting const on the method call, because we don't want it to overload in that way. So I'll just make a little change here. Yeah, we need a little thing here to say, no, I know this is a non-const method, but really the implementation is const. So just a little extra to throw in. While we're on the subject of weird things vector throws at us, we've got at. At's like square brackets, right? You're supposed to call it with something that is less than the size, and it gives you the same result that square brackets would get, right? No. Problem with at is we actually give it defined behavior even when you call it with a great big index. At, we say, throws an exception when you call it with an index that is too large. The index being less than the expected size is not a precondition anymore once you say that. Now, a lot of people look at this and say, oh, well, it's going to be a postcondition because when you return, I is going to be less than expected size. But this is a problem too. The problem is more subtle, but the usual way to achieve a postcondition is to make the postcondition true. This one does not achieve the postcondition, or perhaps by seeing that the postcondition was already true beforehand. This is not doing that. This is achieving the postcondition by killing off every execution path where the postcondition is false. This is using exceptions for flow control. And it becomes a particular problem when you use it inside of some code that may be an assertion that you're going to compile out later because it changes the execution paths in a way that is under the control of the caller. That is a nasty thing to do. I'm glad we don't have a second at anywhere in the library. I mean, yes, it's on some of the other containers, but no, don't do that. This was, this messes up your assertions unless you broadcast that this is one of those things that is using exceptions for flow control. And so I'm going to invent a little bit more syntax there. I'm going to say, yeah, this is a conditionally no return function. Under circumstances that are entirely controlled by the caller, it's either going to be a const function or a no return function, one or the other. I suppose I could put no throw on the first one. But yeah, it has two different ways to go based on a decision the caller can make. And if you do this, then you can look at it and say, well, if I'm going to use at inside of an assertion, I'd better make sure it doesn't hit this branch because that branch will mess up my reasoning. Okay, enough about weirdness of vector. Let's get back to object interfaces where things are nice. See this object interface data? It just sort of runs all the way down the screen here. Where did it come from? Where do you get that? Well, maybe you get it back, you could get it back when you constructed a vector. If you construct a vector, you're gonna need an interface for it to use it. So let's go back to construction time. Zoop. The point where we construct the object interface. And we're going to do this as part of the vector constructor. So here's an interface for the vector constructor. We're going to start by saying we're going to consume some uninitialized memory. Okay, that is weirdness. That is a whole other talk, I think. But yeah, that's still part of the problem. And I suspect that we have to jigger the standard some to be better about uninitialized memory. And okay, apart from that, no preconditions for this particular constructor. There's an implementation, and when the constructor is done, we can say, oh, the expected size of the size we expect is going to be 0. Well, to do that, the object interface has to exist at this point. Where do we construct it? On the caller side, right before the post conditions. That is, as soon as control gets transferred back to us, we construct an object interface And then we can run our post conditions. What does the constructor look like? I'm not going to actually give you the constructor itself, but I'm just going to use member constructors this time. We can, when we are actually going to need to look at the vector to figure out what to expect. We are going to have to say, yeah, I'll make some extra calls at this point and figure out what we're expecting later, because I don't want to fill it in the first time you call size or something. That's annoying. So this is the point where we actually make more calls into the vector. We set up this data. Does the vector need to make all that data, enough data for our interface available? Like, are there going to be preconditions that we couldn't figure out is some method going to have a precondition that we can't figure out whether it's true without some data the vector won't tell us about? There better not be, because there would be no way to ensure that that's true. The vector has to provide enough data to figure out whether you're going to satisfy its own, the preconditions of methods later. Let's go back to here. So we do it, we construct that thing and we say, oh yeah, because it's this constructor, that expected size better be 0. Other constructors, it might be something else. It will be something else in most of them. But for this constructor, it'll be 0. I do want to say, I've been putting all of these pictures on this side. All the code, all of the, like, what's going on. I've been, like, only looking at this from the caller's side. That's something one tends to do with these things, but you got to turn it around sometimes. It's like, well, what's going on in the implementation at this time? How is the implementation making sure those post conditions hold? Especially when the object interface didn't get constructed until the implementation is done. No? The implementation is just going to have to get one of its own. Caller runs their preconditions on the caller side. The implementation runs their the preconditions again on the implementation side. Both can check things. If the implementation feels like checking, maybe it's compiled with debugging off. But if it's checking things, it's doing all this, and it can just construct an object interface right before it evaluates post conditions, check that it works, check that the post conditions works, and throw away its interface. It doesn't have any place to store it. We're not going to make vector bigger to store this stuff. That would have all sorts of problems. Just throw it away. We know how to construct a new one later. And then, okay, when the caller constructs their object interface, it's just repeating what was going on this side. It's very likely, at least, to do the isolation transformer thing and produce an equivalent interface. In equivalent data. So that's the picture on both sides of the line. Nothing about the interfaces crosses the line anymore. We just use separate object interfaces on both sides, and the pre and post conditions talk about the object interfaces that are on their side of the line. The only things that cross the line are function parameters and function results. And if we go back to our inspector call, well, we're going to need to make sure in the implementation, we need to make sure that we can meet the preconditions. So as soon as we enter the implementation, we'll construct an object interface. And then we can do all this stuff, check the preconditions, do our thing, check the post conditions, throw it away. And our object interface, yeah, it should be equivalent because we constructed it in the same way and the vector hasn't changed. But the vector's on our side. That's fine. We made sure it didn't change. Now, I've only done inspection methods so far. Some weird non-const inspection methods, but inspection methods. What happens when we modify something? Well, here's the picture for modifying. I used to think one of the things I really got hung up on for a very long time was, how do you modify the interface data? Like, where does that code sit that modifies the interface data to match a change in the vector? And I think it doesn't sit anywhere. It's just, no, we're done with that interface. We throw it away once the preconditions of our modifier are done. The modifier also does the same thing. It constructs one, evaluates the preconditions, it throws its away. And then we modify things. I want to point out, when we are modifying things, right in the middle of this slide, there are no interfaces to that object. Is that okay? Of course it's okay. No one should be accessing the object while we're modifying it. That's what makes it okay. No one has an interface, they can't access the object. We keep going, we reconstruct one after modification. It's going to have different data in it. That's great. We're in a different state. We'll have the post conditions will depend only on the new state. Throw it away because we have no place to store it. Return control to the caller. The caller constructs an object interface, presumably like the one we just destroyed, and we go on. And we keep going through this cycle until eventually we get to a destructor, and the destructor is just the reverse of the constructor. We do the preconditions, throw away our object interface. I have a question.
Sorry, when we're at a point where we don't have any object interfaces, and then we reconstruct one, where does the information that we constructed come from?
Okay, where does the information that we use to construct the object interface come from? Okay, the short answer, the one for this lecture, is the vector. We actually go back to the actual vector to construct one. The longer answer, the one that still confuses me, there probably have to be parameters sometimes. Weird stuff. If you try to do this for a pointer, you're probably going to need parameters. If you try to do it for atomic things, you might need parameters. Apart from those weird cases, for ordinary sorts of objects, where the reason you need parameters is that sometimes there is data about the interface that isn't stored in the object, that is in fact stored in the execution paths of all the users of the interface. And parameters. And I don't even have syntax there, but need to work on that. Getting back to it, yeah, I think by now you've all looked at the picture. And it's exactly what you would expect. It's the reverse of the construction. We've thrown away all the object interfaces by the time we run post conditions. So yeah, so what does an interface for destructor look like? You'd think kind of the reverse of the constructor. Well, I mean, there's still this uninitialized memory business that got to figure out one day. But there is something more to destroying a vector than this. And the elements are consumed. I chose the default constructor because it was easy. But, don't know how many elements there are when you come into the destructor for a vector. You can destroy it while it has elements still in it. Because no preconditions. But something has to say, we're eating up those elements. Or at least, that's what I used to think it had to say. It's actually worse than that. It's not elements are consumed. It's not the caller loses those elements and they go off into the void someplace. The elements aren't consumed, they're destroyed. And the vector, and with vector, we guarantee that. It's part of the documentation that those elements don't exist anymore. There are fewer objects of that type afterward. And somebody is going to notice it by creating some class like this that whose interface says, yeah, I'm counting the number of objects. Every time I construct one, I'll increment that variable. And every time I destroy one, I'll decrement the variable. And if there are 10 elements in your vector, when you destroy it, that counter has to go down by 10. How are we going to write a post condition that says that counter went down by 10? Did you have a question?
Yeah, but finish your thought. Then I have a question.
Yeah. So there is this general problem of post conditions can't express specific performance. They can express the state you get to, things about the state you get to, but they can't actually say, you did this. And there are times when it's really hard to turn a guarantee about specific performance into just a post condition. Because it's like this, how would you tell from this, how would you write in a generic way? Yeah, if you're counting the objects, there are 10 less now. That's hard. So my solution, at least at this point, is we rewrite this as two parts. The destructor is just an inline thing that the client can execute. It executes on the client side. The client destroys the elements of the vector. And then there's a second half. The client side, as it calls the interface, destroys the elements of the vector. That's specific performance. It just says, yeah, we're destroying those things. And then there's a second part, destroy the internal parts. We'll hide that behind an interface. That's fine. But anything that's specific performance, best answer I've got right now is put it in an inline function, separate it out from the implementation of your class, because you have to put it where people can see it in order to guarantee specific performance. And most of the time it's pretty easy. Insert a range of things. It's actually a little tricky because you have to deal with the exceptions and whatnot. But so there, you have to actually split things into several pieces, I think, in that one. But yeah, what you end up with, because vector does all of these specific performance guarantees about how it manipulates the elements, is all of the constructions of elements, destruction of elements, copying elements, and moving elements. All of that stuff has to be stuck in line where the caller can see it. And of course, if the caller can see all of that stuff, then they'll know what happened to their counter.
And this is how you get all of the destructible warrants for the elements?
Yeah.
That's an input to the destructor, right? Like the client has to tell you, yes, I'm no longer holding any references to this, or they don't matter to me. I'm giving you all the warrants. If the client happens to have an object interface, to have object interfaces for the elements, then the destructor, it's like, oh, I'm calling the destructor now, I have to give up my object interface. I do want to say, I'm not certain this is the last word on this. If in that weird class, I'll go back to it. If in this class we had actually done a proper type interface, the type interface would have had an expected object count. Not a real object count, an expected object count. It's like, this is what you ought to get the next time you ask what the object count is. If you had that, maybe there is some manipulation you could do that would change the caller side expectation and still let the implementation side do the destruction. But I don't know how to do that yet. I'll let this run. Okay, so there's the framework. That's the, that is really, that's the best part of the talk. But, I said I would talk about ways vector throws us confusing things. I'll talk about one more. when you see something like this, I have some constant A. And then later on, I like say, okay, B1 is A plus 10. And B2 is A plus 10. I say that a little later. And these are not supposed to be complicated types or anything. I'm not playing tricks on you here. But you expect that B1 and B2 have the same value after that. That any place you could use B1, they're substitutable. Any place you could use B1, you could use B2 and vice versa. One of them is just as good as the other. Vector breaks this, which is a shame because you absolutely need this for local reasoning. This is the sort of reasoning that lets you say, when I do a calculation, it's just like I did it in my body. It's just like when I did it in my preconditions. You need this property to do local reasoning. But if A is the data pointer for the vector, and you calculate B1, and then somebody brings the size down like that, and B1 it's somewhere out here. It pointed to something before. There's no element there now. B1 has been invalidated. This, we borrow a term from physics for this. This is spooky action at a distance. Whoever had this code, maybe it's running in another thread. You got to do this in another thread, fine. Whoever had that code doesn't even know about vectors. They just have a bunch of pointers. But somehow, this change in size reached into their code and invalidated the pointer. That's even, and when we bring it back up and calculate B2, B2 is a valid pointer. B1 is still not a valid pointer. And yeah, this is a problem. Because, and even the wording around it is weird. We say we invalidated the pointer. I'm not really sure what that means in, a logical sense. Is that we invalidated the pointer value? We changed the pointer value somehow. We're not supposed to change values. We don't go into the Platonic universe that I don't believe in and say, oh, 5 is now an invalid number. We don't do that.
I think we fixed that. I think the whole transparent replacement fixed that.
You think transparent replace? It's so. As of the 23 standard, I am pretty sure this text is still in the documentation for vector. It has we have tried to do some work in core, but we haven't done corresponding work in the library.
Okay. So, but this is a pointer.
This is a pointer,
But it invalidates
vector invalidates pointers.
Oh, that too.
Yes.
Right.
Now it shouldn't do either. Iterators should work like pointers. It shouldn't invalidate either of them in this sense, because that means either you invalidated a value, or maybe it's you invalidated every object with that value. It reached out all through your program, found all the objects with that value and said, nope, nope, nope. And then you have to make new ones. Really, the answer is we have to respect the fact that there's real space out here that can be pointed to in between the size and the capacity. That, yeah, there are no elements. You can't do element operations on things in this space. But we have to admit that it's okay to point to it. And I think this probably came out of overzealous ideas about how debugging implementations of iterators would work, and it somehow got transferred to pointers, and we got to fix that sometime, or else we can't do local reasoning about vector. Yes?
What if the vector gets resized so all the provenances are different now?
Yeah, so if the vector is reallocated, that's a whole nother matter. That means your elements are off someplace else.
And
B1 and B2 might be invalidated.
so
No, A is invalid.
what we would need is B1 and B2 are perfectly okay pointers. They just don't point to things you can access. We have to allow pointers to point off into
Dangling points.
Yes, they are dangling, but dangling only, dangling is it's a lack of relationship to an object. There are pointers that don't point to an object that can be used through them.
Pass them to placement new, right?
If you have control of the unoccupied memory, you might be able to construct something there, yes.
I mean, I'm not a language lawyer or anything, but I wouldn't say that invalidated means that it changes the value. I think it just means that it's invalid to rely on that value in any way after that point in your program.
Yeah, well, what it can't do is change the preconditions of operations on that value. Now, it can change the preconditions for operations on something it points to can change. That's the relationship. But it can't change our pointer math. That's what we have to not do. We have to still be able to do pointer math. And, it's not like that's that hard. It's like, yeah, you add and subtract from pointers. And we don't even have to allow you to address, to add clear out to here. We can set, when we set the capacity, we can say, yeah, you have to stay within this range with your pointer math. And for this pointer that you've got forever, you have to stay within that range. That we can do, that's not a problem. It's just saying that, yeah, we're gonna stop, you're gonna change the range of pointer math that you can do with the pointer you already have. That's the spooky action at a distance. Okay, we do that. And I do want to say that, if we got the change that I would suggest, if you did come back here, yeah, B1 and B2 would both point to the same element here after it gets constructed. Which, we're used to having pointers that, if we do placement new, we have a pointer and it will point to an object once it's constructed that it doesn't point to before that object is constructed. That happens all the time. We're used to it. So I think we can get there. It's these subtle things that get us, though, these things that we worded poorly and we weren't writing carefully enough for code that cause spooky action at a distance. Because nobody actually wrote code that said, yeah, at this point, we iterate over all pointers of this value and invalidate them. Nobody wrote that code. And it would be crazy to think that's what happens. Okay, that discussion is a little technical, bit of a downer. I try to end these things with something that, some larger lesson you can go home with. And I think today, maybe some of the largest lessons, actually, I learned in graduate school. Picture languages, they're great. They have this wonderful relationship between how you say something and what you mean, and that relationship keeps you from saying nonsense. It keeps you from saying things like, I invalidated that pointer value. And you can do proofs with them. So they're strong too. But maybe the more impressive thing I learned in graduate school, and man, this was a hard lesson. But there are times when you have become the world's expert in something. Like when you have written a function or a type, you are now the world's expert in why that function or type is supposed to work. What do you do when you are the world's expert? You learn to explain your reasoning, you write down your explanation, and you get someone to check it. This is what we should be doing, although I'm hoping that one day
we can go one better and say, well, write down your explanation in your programming language as part of your program and get a computer to check it. Wouldn't that be wonderful? Hey, thank you for listening. Are there any further questions? Yes.
Have you given much thought to how you would express post conditions for a method like pushback?
How would I express? Have I thought about how I would express post conditions for a method like pushback? Yeah, those slides turned long. Didn't make the talk. I think I've got some here. Let's take a look. Down past the bottom of the talk, I have slides that didn't make the talk. Oh, look, pushback. Okay, first thing to know about pushback is that it's going to have to be split into two parts because part of is specific performance, the construction part. So we're going to do a pushback without constructing, some private thing, and then a construct at. Construct at is a standard library call, like destroy earlier. Pushback without constructing, actually, I'm going to go and split that into two parts. Sometimes we will call pushback without reallocating or constructing, and sometimes we will call pushback reallocating with constructing. Because really there are two interfaces for pushback. There needs to be this if statement. And it is actually, I think, a shame that you can't do a that you can't explicitly say when you push back that this is intended to be a pushback that does not reallocate. We don't have a way to say that, but we clearly intend it sometimes and not other times. Man, it would be really hard to get that passed through the committee because people would be saying, hey, that has even more undefined behavior than the one we've already got. Why, we can't have that. But it's really the thing you want because you don't want both sides doing this same branch. That's, you don't want to make the implementation do a branch where you already know the outcome. Anyway, you do all that. Do we have another slide? Ooh, yes, pushback without reallocating or constructing is a no-throw method, and it has all of these things. It's like all the old stuff matches except the size got one bigger. So that's something. That's the non-reallocating one. I gotta say, I kind of hate the repetition that happens here. If you gathered them up into a structure somehow, you wouldn't have to do that. This is we need tools that make this amenable to that sort of refactoring. Also, maybe you want to say something like, I only changed these parts. Maybe we want to break it into parts and have a way to say on the implementation, yeah, I only mutated these parts, the other ones I left alone. Because it's better to list the things that you change, because then if you change more, you list more, as opposed to change less and you list more. Okay, the other one, did I get to the next one? Oh, yeah. Pushback reallocating without constructing. This one, we have to say something complicated about what happens to the capacity because we need the amortized constant time expansion. This one, what we're going to do is do a calculation to figure out what would some exponentially growing bound on what the next capacity is going to be, and say, yeah, the new thing that we expect to get back from capacity, if we ever call it, is going to be bigger than that, greater than or equal to that.
You also need to get all the constructible warrants again. Destructible warrants again.
Yeah, I'm not absolutely sure that we can't replace a bunch of that with this. And this is without constructing. This is we're down past that because we did all of that with specific performance.
All right, so that's where we get it back.
Yeah.
But I'm you know, this, I don't know how to integrate this with the Hofeldian stuff I've talked about in the last few years since the pandemic. It may be that they are getting at the same thing, and this is just a more concrete way to say it. I don't know. But that stuff certainly has informed how I look at this.
You have to give this member function the right. I mean, you have to say, I am not going to reference any of these pointers anymore, so you are free to move them. And then then it says you can do these things again until the content.
Well, except that's. Ooh, you're right. I forgot to put in the reallocation step. That needed to be inlined.
Yeah.
Oops. Yeah, I got this wrong. I will say, while we describe it as amortized constant time in the vector documentation, that actually can be broken down mathematically into there is some exponential factor that the capacity has to grow by, that is some minimum for the capacity that has to grow by as you go, and you can turn that into a constant that, it always grows by expected capacity divided by some number, usually a small one, but greater than 0. So you can do it this way. It is a little unfortunate that we don't actually say anything about how you could get hold of this magic constant K. Oh, yeah, these slides weren't finished. D and K are the same.
Yeah.
That's how you would do the amortized constant time business. And Gaspar is right. I totally flubbed if I'd finished the slides, I would have noticed that was wrong. But yeah, I totally flubbed the reallocation there, because you have to the reallocation part has to get the new space and then do specific performance for moving the things over before getting rid of the old space. Okay, other questions? Thank you, by the way, for making me go into the slides I wasn't going to show you.
So I really that was really profound. You about doing proofs in picture languages, because that makes it there's no longer any high priesthood, right? That has to use some other, if you can describe it, you have the tools to be able to prove it, which is an amazing thing. So you're not going to get programmers to think about logical reasoning if they had to learn a completely different language to try to do their proof in it.
Yes. So the question or the comment is that I haven't been repeating all the questions.
No, you don't have to. We're mic'd.
Oh, you're mic'd. Okay. I definitely appreciate the efficiency of only teaching people one language instead of trying to teach them two, and how the two relate to each other. I do want to say, we need a few language extensions. We do need to be able to say things about interfaces and have some assertions in them and whatever. And we also, it is a truism that there is no language. There is no language that will free you from having to clarify your thinking. I am not the first person to say that. And so, it is still, there's a bit of, we have to teach people to clarify and write down their thinking. But I think this is absolutely a skill that if we had the tools supporting it, if we were just routinely writing things that are checkable, it's more or less, not only the same language, it's very much the same sort of skill that we already have as programmers. Just twist it a little bit. There's a little bit more to learn. I think we could teach this in CS 101.
So I I want to double check my thinking here. Our proofs work. I mean, we can do proofs with pictures because everything that we can describe in C++ is constructible, effectively, because we have to construct it to do it. And so then our proofs. Because we never need an existential or universal quantifier, which takes you a higher level up, right?
Mm-hmm. Yeah. And you know, there are other ways of looking at that maybe make it a little more clear. It's actually not possible for code to rely on a precondition that can't be expressed in code. It's, you know, if it can't, you know, if you can't write code that relies on it, to like say you're relying on it, you can't actually write code that relies on it, even in a picture language, because those look so much alike. For people who haven't seen my other talks, which I imagine is a bunch of you, you know, the way people look at things like reachability, the fact that a particular loop is going to end. Reachability is the general case of that. Reachability is a precondition for a lot of our algorithms. And people look at that and say, yeah, you can't express reachability in code. Absolutely, you can express reachability. You can say, yeah, look, this loop, it ends. You can do it by showing it. The thing you can't express in code is unreachability. It's a little weird that way. You can express one, not the other, because recursively enumerable is not the same as recursive. So it's not symmetric with respect to negation. You can't say unreachable in code. But guess what? There are no algorithms whose precondition is unreachability. Yes?
How would you express dereferenceability?
Okay. Dereferenceability is, I think, better expressed as it's not the dereferencing that gets you. It's the, do you have an object interface that you are going to get to by dereferencing this?
So that's where you put the warrants.
That's where you put the warrants.
Thank you.
So you have this collection of object interface. The logical progression here seems to be you end up with in your local context, because object interfaces are like, they're not going, you never pass them to another function. They're staying in your local context. But in your local context, you have a bunch of them. And if you don't have an interface to something, you can't do anything with it.
Is that true? Like if I pass an object reference to another thread, right? I'm effectively saying, I'm also going to give you this interface because until you give it back to me, I can't touch it.
Gaspar says, when you pass an oh, no, you're on the mic. Right. I'm so used to not having that. No, you don't need to you don't do that. You don't pass the object interface. You pass the object and then throw away your interface. The other thread creates its own. It's just the same thing that happens with modern. And you really need that because we can't change everybody's calling conventions to pass object interface data around. It's also, and maybe there is some parameter data that the interface to the function knows about, but yeah, you give up your interface by destroying it. And that's also why you can do this sort of thing without relying on everything in your program and everything outside your program that your program connects to being interface aware. That is, you can have one translation unit that has the checking on, and it's constructing interfaces and throwing them away, and it's not relying on any other translation unit to get them.
So
Yes.
you just trying to summarize what you said to see if I understood correctly. So when you have a pointer and you want to dereference it, you can always do that, but the interface you get back might not be the object you thought you
So,
had.
okay, if I had my druthers, when you dereference a pointer, you get a reference. That's fine. Reference is very much like a pointer. It's like, okay, somebody kick the cable again.
Nope.
Oh, this time I did go to sleep. Right. I got out of play the presentation mode, which puts me in it can go to sleep mode. Okay. If I had my druthers, it would be fine to have a dangling to have a dangling reference also. In fact, you kind of gotta, for the same reason you can have dangling pointers. It's not having the reference that is the problem. It's doing something to an object that you think is going to be there. Mm-hmm. And you can only do something to an object if you have an object interface. And when the thing got destroyed, you threw away the object interface and didn't make a new one. So, okay, you don't have an object interface anymore for that thing. And that's what gets you.
And you know that you don't have it anymore because the destruction was inline.
You know that you don't have it anymore because either, the destruct or is not necessarily inline, but you saw the entry into the destructor. You saw that a destructor was called. Yes.
I have a question about unreachability.
Uh-huh.
Okay, this might be a little stupid, but say we're trying to do list splice. Right, I want to take a piece of the list and move it somewhere else in the list.
Mm-hmm.
But the destination where I want to move it better not be in the middle of the range that I'm splicing. Right?
Yes.
So that sounds like this should be not reachable.
Okay. I'm not quite sure you were loud enough to get picked up by the mic, but this is, you do have situations where you have, where you do an operation and you have to be careful about, if two things that you're working on overlap, you get into trouble, and list splice can be one of them. Another one, mem copy. You get to mem copy in one direction, but not the other. You can overlap one way, but not the other. Or is it mem move? One or the other. You look that up every time you use it. It's better.
The safe one.
And I thought move was the safe one. But it's best to look that up every time you use it. Anyway, the condition there is that you have one pointer that can't appear in this range. That you can write as a loop. It's like, I can compare it to each of the things in this range and say, oh, yeah, it's not any of them, or it is one of them. A loop doesn't end, because I know looping over this range will end. So there is another way to say it that is not unreachability. Yes.
How would you model like a dangling reference? Because like the callee threw away its object interface when it did the destructor, but the caller doesn't know that the reference it received has its interface thrown away.
So we are running out of time now. I think this has to be the last question. How would you model that? The point is that at the point where a function or a neighborhood loses control of an object, it has to know it's losing control of the object. It has, in this case, it was always because it sees the destruction. There are going to be situations that I didn't hear where it's like, yeah, that object still exists, but somebody else has it now. That can happen too. That didn't come up in vector because all of the destruction was specific performance. But so have to have syntax for, yeah, I'm losing this interface and there won't be a new one. But that's basically something that we need to be able to write in
function interfaces is, yeah, there's an interface here that is going away. Okay, well, I did say that was the last question, so thank you again.